So now we are starting with the chemical properties of haloalkanes. So one of the most important property of chemical property of haloalkane is the nucleophilic substitution reaction. First of all, you should know that they are actually reactive. They are actually reactive. Now the question must be in your mind that what makes them reactive? That is the polarity of CX bond. As I told you that the bond is polar, so it acquires partial negative and it acquires partial positive charge. So that means the bond is somehow can break and it can show a certain kind of reaction. So out of that, the nucleophilic substitution reaction are the one which are generally showed by these compounds. And you will see that by undergoing nucleophilic substitution reaction actually give rise to many number of compounds in the chemistry. So just look for that how we can prepare many compounds by using the haloalkanes by nucleophilic substitution reaction. So the general concept is that suppose I have a nucleophile, right, and I have my haloalkane where I know that my bond is polar. So this nucleophile is going to replace this halogen and we will get nucleophilic compound and plus this halogen will be liberated. So this will be the general concept that how the reaction is going to take place. So just look at the board that how we are going to prepare it. So the first is hydrolysis of RX, hydrolysis of alkyl halide, and we will use the hydrolysis by using the aqueous KOH. So what will happen? This R will combine with this OH because we know that this is like that. So this is going to attach, the OH nucleophile is going to replace this X and will get attached to this and we will have the alcohol. So that we can have the alcohol by reacting with aqueous KOH. For example, suppose I have CH3Cl. I am adding KOH, again it is going to break like this and it is going to break like this. So my OH is going to attach to CH3, so I am going to get methanol and along with that I will get the KCl. So this is what is the hydrolysis of alkyl halide. Next is with KCN. So suppose I have an alkyl halide, I am adding KCN, I know this is my nucleophile and this is my positive group and this is my halogen. So this cyanide is going to replace halogen. So I am going to get cyanide plus Kx. So this is something a cyanide group, right. Now this from this cyanide group is an important group compound and we can by using this cyanide group we can further prepare many compounds like I have this RCN, I am doing its reduction in presence of nickel and you know that when I do like this what I get this compound that is the amine. We are able to get this amine and this kind of reaction where we are preparing the amine by using the cyanide by carrying out the reduction in presence of nickel of cyanide, that is something called as Mendeus reaction, that is called as again a name reaction, that is the Mendeus reaction. Now we can also carry out its the hydrolysis controlled and uncontrolled. So this is the controlled hydrolysis where I have used the hydrogen peroxide. So where here I am going to get is amide. Here I am going to get the compound that is the amide. And when you carry out the complete hydrolysis in presence of any dilute acid, what do you get? You get a carboxylic acid. You get a carboxylic acid. So that means you can just by from cyanide you can prepare amine, you can prepare carboxylic acid, you can prepare an amide. Next we are adding AgCN. So let's say that our alkyl halide is Rx, I am adding AgCN to it. So in this case this is my nucleophile, it is going to replace X. So what I will get, but we know that this is an ambident group, that means it can attach this way also, it can attach this way also. So when you react with AgCN it is going to attach in this way and we are going to get, instead of cyanide we will get an isocyanide. We will get a isocyanide. And next is the reaction with sodium alkoxide. So this is my Rx, sodium alkoxide is, let's say some alkyl members, say let's take methyl sodium methoxide. So in this is going to be my negative nucleophile CH3O and this is going to be, so this will replace this, so it will form OROCH3 plus NaX. This is something ROR, that is ether. And the process of forming ether by adding sodium alkoxide to alkyl halide is something called as Williamson's synthesis. Now with AgNO2, Rx plus AgNO2, in this again my nucleophile is NO2, this is going to replace this. So I have this RNO2 plus AgX, that is the nitroalkane. So you can prepare the nitroalkane by this method. Next, we are reacting it with sodium acetylide. We know that sodium acetylide is a compound where sodium is attached to the acetylene, and what do we get? We are going to add Rx. So here what is going to happen is that this R is going to replace this N. So what you will get? You will get R, C triple bond, CH plus NaX. This method, actually I told you in alkynes also that this is a method by which you can use the acetylene for preparing the higher alkynes. So this is used for preparing the higher alkynes. Now with ammonia actually it show a monolysis. See how? Suppose I have some alkyl halide, let's say this thing, ethyl iodide. I am adding ammonia to it. So whenever we add ammonia, we know that this thing NH2 group gets attached. So this is what is this going to form? Ethylamine. This is ethylamine. Now this ethylamine can further show an monolysis. That means we can use this ethylamine. We can add more alkyl halide to it. And what it will do? It will now become, it will again replace, it will form C2H5 whole twice NH, because here it has been replaced by adding one C2H5 group again. Now again it has one more replaceable H, we can add more also. So we have C2H5 whole twice NH plus again C2H5I. So what do we get? C2H5, now it becomes thrice and it becomes N. So likewise you can do it. So it yields the primary, it yields the it yields the primary, it yields the secondary, it yields the tertiary amines. So this is what is the reaction with ammonia, showing the ammonolysis. Last is the silver salt of carboxylic acid. So whenever we react with some silver salt, let's say CH3COAg, I am reacting with Rx. So what I am going to get is, so this is my acetate group, right, and this is mine. So this is going to attach here. So what I am going to get here is CH3COOR plus AgX, that means RCOR ester. So as you saw that it can undergo nucleophilic substitution reaction to a great limit, and it forms many kind of compounds, as we saw that by using KOH we formed alcohol, by using KCN we formed cyanide, then further by using cyanide we form amine, amides and carboxylic acid, by using AgCN we prepared isocyanide, with sodium alkoxide we prepared ethers, and with AgNO2 we prepared nitroalkanes. With sodium acetylide we can prepare higher alkynes, with ammonia we can prepare many primary, secondary and tertiary amines, and with silver salt of carboxylic acid we prepare an ester. So you can see that this thing haloalkanes are actually undergoing the nucleophilic substitution reaction to a great extent, and the reason behind that is only that the bond between C and X is somehow polar, right. So that is why if we have any nucleophile which is more reactive than X, it can just take the place of X and we can get so many compounds. So this is what is the first chemical property, that is the nucleophilic substitution reaction. And one more thing, as far as the name reactions are concerned, I am telling you again, the Mendes, the Willemans synthesis, ammonolysis, you have to keep in mind, because these reactions form the base of the chemistry, organic chemistry, right. So this is what is the first reaction, nucleophilic substitution. Now we are going to start with the further reactions.